Good morning, friends. Let's continue our discussion about designing a very simple dummy type of TCP-based order management system server. In this server, which we are working for last previous videos, that we are building a TCP server and receiving stock trading orders from various clients. Once the order is received, then we actually we parse that request from the wire, and then we create an order object out of it. And after that, we do a lot of steps. And we have just mimicked it that, for example, validating the order, it will take 1 second. And reaching the order with the latest market data will take another second and all. So there are various steps, and all these steps that we counted out, it was actually taking 6 seconds to parse one client order and send it to the downstreams after doing all the validation, enrichment, and updation to the persistence. Then we came up with the very first approach of having a single threaded blocking OMS, in which our server or the OMS server was listening on a port, and then we actually had a infinite loop until the server socket is closed. And we actually there was one thread, the main thread, which was blocking here on the accept method. And as soon as a client is connected to our server, the same thread which has been accepting it, the same thread will handle that client request. And that handling, as we have described in this method, it will parse that socket object to create a request object first, and then one order object. And after that, we will have all these steps until it's sent to the downstream. And we have already seen that all these steps take 1 second. For example, creating a request and then creating an order out of it. And all these steps that we have mimicked it to take 1 second. So if we count all of this, it will take 6 seconds to serve one client request. And because this is single threaded, which means that there is one thread which is accepting the orders as well as handling the orders as well, handling the socket as well. It will take, suppose there are 3 requests sent at the same time, then only the first request will complete in 6 seconds, and then serially the other 2 requests will be served in 6 seconds each. So it will be total 18 seconds for serving 3 client requests in this single thread design. In the second approach, in the better approach, we wanted to improve this performance of this throughput of it. So we came up with a new design of thread per client OMS, which means that the thread which is listening on the client server socket requests, as soon as a client is connected to it, it will create a new thread to handle that client. This is the step. And after creating this new thread, which is supposed to handle that particular client request, the main thread will again go back in this while loop and then again listen for another client request. So by doing this, actually, this became the handling of the client socket request was delegated to a new thread every time. So suppose if there are like 10 client requests sent at the same time, there would be 10 new threads created to handle each of these client socket requests. And so by doing this, because we are like parallel, it's like more of a concurrency example, where each of the 10 clients requests can be handled at the same time if we have got 10 cores in our system. So in that case, it massively improves the throughput of the system. So it would be like if like all the 10 clients are served at the same time. In that case, it would be total 6 seconds to taken for serving all those 10 clients. So this was our design for thread per client OMS. But as we have discussed in our previous videos, that there are like quite a few caveats here. First of all, I mean, if we are creating a new thread on the fly, there can be too many threads created. And just notice that all these threads are platform threads, which are bound to the OS kernel threads. And always there are a limited number of OS kernel threads available in our system. So that's why if we are creating too many threads, we actually went through an example that we are creating 100,000 requests at the same time, which means it was creating around 100,000 requests. It tried to, but after say 400, 500 threads, which is the limitation of my laptop at the moment, it starts crashing because we cannot create so many threads, platform threads at a time. That's why threads are scarce, and this is a limitation imposed on the maximum number of threads which can be created in an OS. And another thing is that there was a single thread, this thread which is actually doing all this like steps for handling this request in 6 seconds. We can there's a small scope that we can improve this performance by creating more threads to handle this concurrently. Instead of one thread doing all this like 6 seconds of creating the request, validating, enriching, and persisting. What we can do a small optimization is that we can actually do it in a concurrent way. We can have more than one thread to handle this socket request. So this is where we come up with the third approach, in which we will be handling this request by multiple threads. So let's go through this class. So all this part is same, that there would be a server socket which would be accepting it for the next client request, and whenever we receive a client request, it will be creating a new thread. Now inside this handle method, this is where we have made the changes. So first of all, once this thread is created, and then we parse this socket object to create our request, and from this request we create an order object. So these two steps will take 1 second each. So from at this point, there would be 2 seconds already spent by the thread which is handling it. After that, we create more threads to handle the validation and other parts in a concurrent way. So let's go through this get part order parsing threads. So we pass this order object and the request object, and after that, we create 3 more threads to handle the validation part, the enrichment part, and the persistence part, to update it to the persistence. This all would be done in separate 3 threads. So now these 3 steps, we are trying to parallelize it. So once we create these 3 new threads, so we have to start it here. So this is what we are getting. We are getting 3 threads for validation, enrichment, and persistence. And then we start all these threads in parallel by calling this t.start. And after that, we wait until because we have to wait before we send order to downstreams, because we need to validate, enrich, and persist it. Only then we can send it to downstream. So here, this process, I think this will be, if all the 3 threads are done at the same time, so it would be, so all the 3, if there are like more than 3 client requests, it would be all done at the same time. So this is where we can reduce the time from, say, 6 seconds to maximum 3 seconds. So this we will that's why I have got this performance benchmark here, and we will see that how much time it will take after parallelizing these 3 steps. And once we send it to a downstream, it will take another 1 second, and then this will be done. So this is a very good improvement over the previous one, where there was a single thread which was doing all this handling of one client request. Now we have parallelized these 3 steps as well. So if we count the time, that how much it will take for one client request to be handled. So there would be 1 second plus 1 second, 2 seconds. And here it will, because it is all done in parallel, so it will be again only 1 second each. So 1, 2, 3, and then 4. So theoretically, it will take 4 seconds. Previously, it was taking, when we were dealing it like for one thread handling all these 3 things, it was taking 6 seconds total, right? Because we are not validating, enriching, and persisting parallelly at the same time. But after this improvement, we expect that it will take from 6 seconds, it goes down to 4 seconds. So this is what I have mentioned here. So it will take a request, order, and then max of 1 plus 1 plus 1, which is enrichment, validation, and persistence. And total will take 4 seconds. This pattern is sometimes also known as fork join or scatter gather. So this is all theoretical. Let's try to run our socket client program, which we have discussed before, in which we will try to create a lot of client requests at the same time based on the parameters that we are creating. So I will start with 4 client requests at the same time, and then try to increase the number and see that how it actually performs, and what is the benchmark, whether it actually reaches 4 seconds or not. So let's start our program here. I click on the run button. So we expect that it should take 4 seconds each for serving each client, because we are parallelizing that steps. And after that, I will also run this socket client 4, which is trying to connect 4 client requests at the same time. So once I run this, so let's see. So started this. So it has sent 4 requests, and let's see how much time it took here. So we can see that each of the order which is sent to the downstream, it takes around 4 seconds. So theoretically, whatever we expected, that the time it should take for each class to be served is around 4 seconds. One for creating the request order from the socket object, then creating an order out of it, and then we had 3 threads doing it at the same time, which is a validation, enrichment, and persistence. And after that, sending it to the downstreams. So it took around 4 seconds each of them. So theoretically, this is all correct. So here it will work as expected. But again, as a limitation, as we have seen that because we are creating all the threads on the fly, there are too many threads created now. Instead of creating like one thread in the previous example, now it is creating one thread plus it is creating three more threads for each client request. So there are total like four threads already there. So if I try to like run, say 100,000 client requests at the same time, then it will again have the same problem because our system cannot create so many of platform threads because of the limitation imposed by our OS. I just clicked on this 100,000. As you can see that after a certain time, it stops and we have got this connect exception. However, we can see that there's still an improvement that from previous 6 seconds, it's taking 4 seconds now by parallelizing these three methods. But besides that, there are a few more caveats that in this design. First of all, because we are running this validation, enrichment, and persistence in separate threads, so we have to ensure that these are thread safe. So we have to ensure that these are like synchronized, or we are using some like locking mechanism so that it's all thread safe. So we have to introduce this synchronized method in all this invalidate, enrichment, and persistence methods. So this is something that will actually needed that because concurrency is not comes with all these like thread safety issues. So we have to ensure that every time we are ensuring that our methods or the critical sections are always thread safe. And another caveat is that because now we are creating so many number of threads, uh, every time our client is connected, we create a new thread. And inside that handling of that request, again, we create three more threads each time. So total, there are like 4 n threads for each one client connection. So for example, if there are like n simultaneous connections, there could be 4 n threads created and destroyed each time. Here we can do another very, very small optimization that instead of 4 n threads, we can just create 3 n threads per request. How we can do is that we can actually just use, okay, so we have got this one thread which is handling this, right? So, the thread which is created by in the main method, and that thread would be creating this request and order. Then instead of creating 3 threads from this, what we can do is that we can just create 2 threads, one for validation and one for enrichment, and the same thread which is handling this, and that should be continuing with the persist method. So this persistence is done by the same thread which has been creating this request and order. And only these 2 threads for validation and persistence validation, that would be done in parallel. So by creating this and not creating 3 threads but using only like 3 threads at the time, we can still parallelize this, and then finally we can join all these threads before we send it to the downstream. So by doing so, there is no change, but what we are doing is that we are reducing 4 threads to 3 threads because we are treating the same thread which is handling this request to also persist the order at this step. So again, this is just a small reduction, but for the latency, it would be still 4 seconds because we are just reducing the threads, but still all these 3 operations are done parallelly by 3 threads. So if theoretically, again, it designs slightly better that we are creating only like 3 n threads each time for each client request, but still the time to process would be same. Like it will take 1 + 1 for request and order, and then for the 3 steps, it would be done by 3 threads at the same time. And that's why it will be still 4 seconds. So this is the actual code here, as I just demonstrated. So this handling thread, which is created, this thread is actually creating the request and order, and it's also persisting it here. And then we have got 2 parallel threads at the same time, which is one of them is validating and one is enriching it. So still we have got these 3 operations in parallel, but just that from 4 threads we have reduced it to 3 threads. And then once we join it and then send it downstream. So let's run this and again try to see that whether it's actually 4 seconds or not. So I will run this, and after that I'm just going to get ready for my socket client 4 connection. Okay, so my thread is listening on this. So let me close the previous one, and let's run this. So we expect that it will again take 4 seconds. It's just that the number of threads have been reduced from 4 to 3. If I see this, now we can see that again, it's 4044, 4031. I think that it's like very slight improvement as well in the latency. I mean, earlier it was taking around 405 and 4056 something. Now it has reduced to 403 something. Anyway, so it's still 4 seconds. And if I run 100,000 clients at the same time, so again, we expect that they should fail because we have always got a limited number of threads. So I just click on this 100,000 and I expect that after a certain time, it gets connection refused. Okay, so this is what this our approach for parallelizing the order handling part. We have improved the performance from 6 seconds to 4 seconds. All this design is better. Like thread per request style is the best way, but we are always marked by uh, the number of threads that we can create at a time, the number of platform threads that we can create at a time. So let's improve this design by in the next video we'll see that we can control these threads by creating thread pools. Thread pools has been a concept which came from Java, I think 1.5 version. After that, it has dramatically increased the way that we treat and that how we actually handle all these type of scenarios, where we can control the number of threads that we can create. So see you all in the next video when we'll come up with the thread pool based OMS.